400 kilometers above our heads, a new NASA detector orbits around Earth at 28,000 kilometers per hour. Initially planned to investigate mineral dusts using an amazing technology, its first data shed a new surprising light on greenhouse gas emissions. This new telescope allows to detect and track large-scale emissions directly from space, which was until now close to impossible from the ground. And it does much more than that. Today, we delve deeper into the amazing science and technology behind EMIT. We explore the world of opportunities it opens and how you can access its data and support its science.
3, 2, 1. Engine ignition. And liftoff.
The 14th of July 2022, EMIT took off aboard CRS-25 Dragon resupply mission from the Kennedy Space Station in Florida. Everything went nominal: the launch aboard the Falcon 9, the successful booster landing, and the successful rendezvous with the International Space Station, the final destination of this telescope. The reason EMIT was sent to the ISS is to benefit from its power and data links. Also, to some extent, it's a free ride, since the ISS is already there and needed resupply. But the most interesting part for EMIT journey in the ISS is its orbit. Despite being somewhat erratic, its orbit hovers over the most important dust sources of the planet. Mineral dust is one of the biggest travelers on Earth. Strong winds steer it up from the Saharan desert or from the steppes of Mongolia. They then travel for thousands of kilometers away. Once airborne, these particulates can heat or cool the atmosphere, affecting the weather and climate, for example by shading solar radiation. The clouds they form can also reduce visibility and impact human health. However, these particulates are important to the environment. When they settle inland or in water, they can provide important nutrients to entire ecosystems and allow their growth, and their volume will increase with climate change. While scientists know these dusts come from arid and dried regions, they don't know their exact composition. And this is important, since different minerals affect ecosystems differently and heat and cool the atmosphere differently. EMIT's primary mission is to analyze these dusts, their dynamics, and characterize their composition. These data will then feed climate and weather models and improve scientific knowledge. To succeed in this mission, EMIT uses an amazing technology, an imaging spectrometer. Photons are not only particles. They also behave as waves, carrying energy which makes them oscillate or vibrate. Photons therefore have multiple wavelengths, or colors if you prefer. The Romans were already familiar with the rainbow generated by a prism. Many authors cite prism usage to split light into multiple colors, and archaeological studies found pearls deliberately cut in prismatic form as far as in Thailand. But the scientist who is traditionally regarded as the founder of spectroscopy is Newton, although he was not the first scientist to study it. He demonstrated that colors are components of light in his research treatise Optics, which was published in 1704. However, it was not until 1802 that a chemist, William Hyde Wollaston, discovered what was going to be the most important principle for spectroscopy. Joseph von Fraunhofer independently discovered the same 12 years later and gave his name to the Fraunhofer lines. When the sunlight is projected through a prism on a screen, the resulting rainbow misses certain patches of colors, which show black in the projection. This is caused by the elements within the sun itself, as well as Earth's atmosphere, interacting with light. However, light spectrum is much larger than what we and Newton could see with the naked eye. Different wavelengths of photons get absorbed by atoms, depending on the energy they carry. And not only atoms, but also molecules have their own specific light signature. This is called the spectral fingerprint. That same interaction with electromagnetic radiation or light is actually the main mechanism causing climate change, as water vapor, carbon dioxide, methane, and other big molecules absorb infrared lights or heat. Spectroscopy takes benefit of these interactions to characterize materials by studying the light they absorb or they emit. Nowadays, this same science can be used in diagnostics and treatments in the medical sector. X-rays are one example, but also infrared as well as other wavelengths could allow non-invasive and non-destructive opportunities for visualizing complex chemistries, detecting lesions or cancers, and intervening on specific organs with no surgeries. But the most spectacular use of spectroscopy is in space exploration. It is used to analyze compositions of comets and even other worlds. The James Webb Telescope uses spectroscopy to analyze old stars and galaxies' compositions, but also exoplanets' atmospheres. By comparing light signature from a star with the light filtered by an exoplanet atmosphere, scientists can characterize its composition. JWST has recently discovered water, sulfur dioxide, and even CO2 in a system of exoplanets only distant by 700 light-years from us. After Dragon had docked with the ISS, astronauts carried to offload food, water, air, and a bunch of scientific experiments from the pressurized compartment. But on the other side of the capsule, exposed to the void of space, EMIT and its instruments had to wait their turn in the Dragon's trunk. After few hours of very delicate maneuvers by the Canadarm, EMIT was installed and ready, pointing its telescope towards the Earth. And when the show started, the first shots turned out to be amazing. What we see as homogeneous colors with the naked eye turns out to be very diverse and rich scenes under the eyes of the telescope. EMIT images cover approximately 70 kilometers wide with a resolution of 60 meters per pixel. Each and every pixel has its own light signature and can be analyzed to characterize the composition of materials and dusts. Among the pictures, there are some spectacular ones like these taken around Lake Mead. We can see here the mineral diversity of iron oxide contents, other sets of different types of minerals seen in different wavelengths, as well as different types of vegetations and their status. But this is only one part of what EMIT was able to do. The light spectrum EMIT can study includes wavelengths from 380 to 2500 nanometers, corresponding to visible light and part of the infrared spectrum. Therefore, EMIT can also detect light signatures from methane and CO2. This means with the help of EMIT, the methane emissions sources can be characterized with precision. Methane has many natural sources like wetlands, certain insects like termites, or even permafrost that is thawing rapidly because of global warming. But there are also human sources of methane like industry leaks, extraction, agriculture, and waste management. Methane is much more potent than CO2, since, depending on the conditions, it can generate more than 80 times CO2 greenhouse effect. Reducing methane emissions is therefore key to reducing global warming and delay its impact. EMIT does from space what remains complex to do from the ground, especially for industry. There are norms to limit emissions in majority of countries, but enforcing them is difficult. Although advanced and efficient optical technologies exist, such as cameras allowing to detect and quantify leaks, using local ground detection requires monitoring entire installations all day long, involving high labor and equipment costs. And while emission norms still remain to be followed, methane concentration in the atmosphere has already grown by 160% since the pre-industrial era and is still growing. This is why EMIT opens a new world of opportunities. While this is not the first time that spectroscopy analyzes methane from space, as both NASA and ESA already sent satellites capable of doing so, EMIT's resolution is the real new feature for me. since it allows to pinpoint emission sources and calculate their volume with high accuracy. This is why EMIT is only the first step. NASA and JPL engineers are also thinking to adapt the same technology into other missions to study the entire globe, pinpoint emissions and their sources, but also study more accurately other components like volcano ashes and use them to build volcanology predictions. Until these missions launch, EMIT will continue helping scientists to better understand the effects of dusts and the mystery of methane emissions and address the artificial ones to answer the many questions scientists still have. And by the way, you can help uncover these opportunities whether for analyzing dusts, emissions, or even coming up with other use cases for this detector. NASA made these data publicly available with free registration to get support on analyzing and advancing science. You can access it easily, the same that I did, and participate to the studies. Links are in the description.
Hey, don't leave yet. I still have something to tell you about EMIT. But before that, I'm late. I did not imagine the sheer amount of work that is necessary to produce such quality videos. Let me know what you think in the comments and if you have any ideas that I could cover next. About EMIT, there is an application that could be very interesting, tracking hydrogen emissions. I'm not even sure that this is possible with EMIT, but it could help mitigate its greenhouse effect. Surprised? More on that on this video. My name is Khalid and I talk about interesting science.